Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internal.
Hello, I'd like to welcome you to the second industrial keynote that we'll have here at IEEE VIS. I want to introduce you to Jim Jeffers. So Jim leads the Intel's advanced rendering and visualization team, developing open source software, rendering libraries used for generating and animating movies, special effects, automobile design, and scientific visualization, working with companies like Disney and DreamWorks, plus scientists like Stephen Hawking. Jim joined Intel in about 2008, participating in the development of the multi-core parallel computing and in the Intel Xeon Phi product line. He's been active in publishing. He's co-authored 4 books on mini-core parallel programming, and his experience includes software design and technical leadership in high-performance computing. And so we're really pleased to have Jim here. And so I'll hand it over now so that Jim and the Intel team can give us a brief discussion, and then we'll move on to questions and answers.
Okay, thanks. Looking forward to it.
Hi. Before I start, I'd like to thank Valerio, Pascucci, Jim Ahrens, and Chris Johnson for arranging for me to deliver this keynote address. I'm Jim Jeffers, and I lead the development of Intel One API Rendering Toolkit. My role and goal in the industry is to unleash your ability to achieve the most effective visualizations you can, with as few constraints as possible. Today, I'm going to give you a quick update on what we and our collaborators have been doing this past year, and also where I think we're going moving forward. No keynote would be valuable without a look at industry trends. For my part, I call the current trends exatrends, with us being on the doorstep of exascale. At a billion flops per second, the big data era is shifting to massive data. This massive data needs efficient mechanisms like ray tracing to better make sense and effectively analyze that data. Computational capability is growing much faster than I/O, increasing the need to analyze the data in place, in memory, as it's generated, or in situ. And if ray tracing is already there for better visualization, why not use its heritage in wave and particle physics to lighten the load for relevant compute codes? A continuing trend is towards open standards to help developers and researchers get more out of their time investments in algorithm and code development, and to access new hardware without rewriting code for the specifics of the platform. 2 emerging standards are the Chronos Inari standard that promises to provide a flexible middleware interface for rendering that is cross-vendor. The other is Intel-led One API specification that provides similar cross-vendor and cross-processing architecture applicability. For professional rendering, the Academy Software Foundation continues to curate key standards. Another trend that I see is the movement beyond heterogeneous CPU or GPU computing to platform XPU cooperative computing. For example, these are some of today's typical GPU accelerative features within a fairly limited direct access memory footprint. Now, our render kit has a broad set of features available today with many benefits and large memory footprint of CPU platforms. Our goal is to solve this disparity via an XPU cooperative platform focus. Here's how. Over the last 18 months or so, Intel has been revamping its focus to a more holistic platform focus with 6 key technology pillars across 4 computing architectures: Our mantra for this focus is no transistor left behind. The One API initiative is growing rapidly with the goal of being open, but also cross-platform and cross-processing architecture, covering CPUs, GPUs, FPGAs, and other specialty acceleration solutions. Our goal, no developer left behind. Now a very quick don't blink update on Rendering Toolkit. Here's a snapshot of the family of software components that make up the One API Rendering Toolkit. As you might imagine, given what I've said earlier, a key initiative on my team is to use our future Xe GPUs for even greater platform performance. I'm also excited to announce the recent arrivals of Osprey Studio and our Osprey plugin for the USD Hydra interface. Finally, our goal for you is no pixel left behind. Here comes the don't blink part. I'm going to quickly step through the ever-growing capabilities of RenderKit components. Gold highlights the new and improved features since last year. For Embry, Quaternion Motion Blur is my favorite. For OpenVKL, VDB data format and multi-attribute data are game changers. For OpenImage Denoise, you have access to the AI training infrastructure to tune the denoising to your uses. For Osprey, realistic sun-sky models and panoramic 3D stereo are very cool. We're having really great success with our Intel Graphics and Visualization Institute's collaborations. For instance, our Osprey Sun-Sky model comes from Charles University. Now I'll give you a sneak peek at some of the VIS demos we'll be doing at SC20. Climates and its impacts on weather from Nicholas Robert and collaborators. We'll show a live screen capture of a 1.3 terabyte dataset on ParaView using Intel Optane memory. This is an SC20 VIS contest finalist. Another SC20 VIS finalist from the Intel GVI at NIU and Argonne National Labs, running live with ParaView visualizing blood and tumor cells circulating around a microfluidic device. This is really cool. We'll be showing off the just released Catalyst in situ Optane memory temporal cache capability off of Tax Frontier, a supercomputer. Last but not least, and literally hot off the presses, we'll be showing the latest in black hole and gravitational wave theory, showing that some black hole collisions don't result in a merger, but they bounce off each other and accelerate away like rockets. Okay, my time's running short, so I'll quickly wrap up. This eye chart is all your host SC at Utah's Intel GVI related submissions to VIS. Check them out, especially Meng Zhao's tiled display walls. Too quick for you? Head to bit.ly/renderkit to learn more. Hopefully this talk makes you feel like our industry collaborations are letting you unleash all your technical potential. And don't forget the mantra, no transistor left behind, no developer left behind, no pixel left behind. I should be available now live for any questions. Thanks and stay safe.
Well, thank you, Jim. So I think you have Discord open, so maybe based upon questions that come in and how you want to organize them. I can't hear you.
I wanted to double
There we go.
check. I didn't, so I muted. Unfortunately, I don't have Discord open because it took me too long to log in, and
Okay.
I have no technical ability, so I'm very challenged there. So you may have to read.
I don't see any questions yet.
Okay.
Coming into chat.
That means I had a perfect presentation.
Well, we are getting, we are certainly getting some statements by viewers that said that they appreciated it.
Okay, that's very nice. Thank you, everyone.
I guess in terms of the, trying to make sure I get all the statements right. No transistor left behind, no developer, no pixel.
Yep.
I think all of those make sense. Now, if you're trying to be prescient and try to predict, understanding that your predictions are not in any way obligating until what might be other things that we are leaving behind that you think we could capitalize on. So certainly you've picked three great ones.
Yep.
What do you see in the future?
Boy, that's a great question. I do think there pretty good coverage. You've got a platform, so I think the key or a key or something to really look at is the no transistor left behind. That's way easier said than done. Today, for instance, with today's GPU acceleration, there over the last 5 years, I have to, more and more utilization of those, particularly in HPC environments. I mean, we can talk about a variety, but I'll stick with HPC supercomputing environments. They continue to grow in capability. When we come out with our discrete Xe GPUs, we hope that we, hit the nail on the head for programmability. But frankly, they're fairly dramatically different platforms from a CPU platform, what it targets, GPU platform, what it targets. And of course, there's this melding of trying to, hit a crossover point between them. So, we really are focused on my team in particular for the rendering toolkit as hopefully an exemplar of that notion of no transistor left behind, which I'll be frank is a visionary statement, and so, but when you come down to that concept, whether you argue whether Moore's law is slowing down or what have you, with the new process technologies, smaller and smaller, more and more transistors. How do you touch those? How do you light them up? How do you do it in a way? And the way you do that is through really, really smart software, really intelligent software. So what I see is today, this is a little bit aspirational, but it's a vision and a work focus that we have at Intel, at least. So, and the three things to me, particularly in VIS, go hand in hand, right? We have to offer developers the opportunity to touch those transistors through great software interfaces, through development tools, and then, from a pixel standpoint, I'm basically referring to, in particular, ray tracing, which I think has been growing steadily over the years. Obviously, for film, it's 100% ray tracing for any 3D stuff. And I just think we're just going to see that actually hit a hockey stick type rise in the next couple of years.
Okay, thanks. There is a question concerning whether your slides will be available. So that's something, I guess, for you to decide.
Slides are public. Yeah, I don't. Obviously, the talk I just did is, I guess, going to live for a while. You guys will have to say how long it lives. But I went over it really quick. But if you go to, there's a long Intel URL. But if you go to bit.ly/renderkit, we will look to post those, publicly available slides, over time. Okay. So I would say, if you want to understand where we're going and some of the background on the slides, that we will post more and more at bit.ly/renderkit. And actually, we just put up a new website about 4 hours ago, or an updated website.
Okay, so one other question that's come in, probably will be our last question. How can Intel best continue to enable VIS research? What are the areas that software and hardware could be improved?
It's a multi-pronged effort. And we are engaging the ecosystem. The One API initiative that I talked about in the talk is my product area in VIS is called One API Rendering Toolkit. So, we're looking for academia to embrace that. We're supportive. We're here. You can, IM me, text me, Twitter me, whatever the right thing is. We'll try to get it. And then I would really go back to, again, in my talk, look at those 7 institutions now. We may be growing. We'll see. In the Intel Graphics and Visualization Institutes. So I'm pretty happy with our goals and support there for some of the key players in visualization, both on the compute and like cosmology with the Hawking team, Texas Advanced Computing Center. Paul Navratil is an NSF leader. And we also work very closely with Argonne National Labs and the DOE, Jim Ahrens and folks. So I think follow what we're doing. You know, I'm not a big person for this, but, you know, follow me on Twitter if you want to, at James L. Jeffers. I am called Jim, but that's unfortunately what I could get because of my common name. But yeah, I would follow us there, reach out to us. There are many avenues that, you know, whether you know my email address or not, that you can get in touch with us. But, you know, Chris Johnson, Paul Navratil, all those PIs, go back and place a still on those and reach out to those folks. They are kind of the academic leaders that we're working with day to day, and they're very open to discussions and you know, getting together. And again, I'm glad you're here at IEEE Viz. This is one of the places where we try to show you what's happening.
Okay. Well, thank you very much, Jim. And as thanks to all of you who attended. And as you heard, Jim is very open to you contacting him if you're interested in more about what he presented or Intel in general. And these, we thank you very much.
Thank you. Thanks, everybody. Again, stay safe. Good luck and enjoy the rest of Viz. And see you at SC20. I'll be around again. Actually, really quick, SC20, we're going to have live, like a live Intel booth where people will be manning it, including myself. So if you want to have a verbal conversation with me, that's a possibility in a couple of weeks. Look up for the Intel stuff there.
Great. All right. Thank you very much. Okay, bye.
Yep.